Hello students and welcome back to another episode of microwave spectroscopy. Up till now we have discovered what are the assumptions in microwave spectroscopy that we need to take care of, and so far we have derived an expression regarding the moment of inertia of a rigid diatomic molecule, which we also refer to as a rigid motor. Okay, so the moment of inertia is equal to mu r square, where r is the bond length or the bond distance between the two masses. Okay, and mu is the reduced mass. Right, now as far as the energy of this particular molecule is concerned, which is rotating about an axis, then the energy of such a molecule is given by h square over 8 pi square I multiplied by j into j plus 1. Now we don't need to go into the details of derivation of this expression because that actually belongs to your higher studies section, and this energy actually is in joules. But when we talk about the spectroscopy, when we discuss the energy with respect to the spectroscopy and the EMR and the techniques related to that, we don't refer usually in terms of joules. We refer the energy in terms of, we consider it in terms of centimeter inverse. Why? Because we correlated with the wavelength and the wave number. Okay, because it is one of the property of the electromagnetic radiation. Okay, so we will try to convert this energy into centimeter inverse first, and then we'll go further. Before moving to that section, what these individual terms mean in the expression, actually let's write down. H is the Planck's constant. H is the Planck's constant. Pi, you know, it is a constant value. I is the moment of inertia of this particular molecule that we are talking about, and J is the rotational constant, or you can also say it is the rotational quantum number. Okay, which can be 0, 1, 2, 3 and so on. So this is J. J is the rotational quantum number or the rotational constant. I is the moment of inertia, and E is the energy over here. Okay, now let's try to convert it into the centimeter inverse form. For that sake, you know already the Planck's equation, which says delta E is equal to h mu, which is equal to hc over lambda. Okay, so if I just take lambda as it is, I can write it like 1 upon lambda is equal to delta E over hc. Okay, so actually 1 upon lambda is what? It is mu bar, which is the wave number, right? So this expression actually will serve or serves as the conversion factor. Okay, so now I substitute this part in my equation number 1 over here. How do I do that? So it becomes E, I just divide both sides by hc because I want to convert it in terms of centimeter inverse. So E upon hc is equal to h square upon 8 pi square I into hc. Okay, and multiply this whole by j into j plus 1 factor. Now this h and h gets cancelled over here. So E over hc is equal to h over 8 pi square I into c into j plus 1. Now this actually is the energy in the centimeter inverse. So we can write this expression as energy, okay, is equal to h over 8 pi square I c into j plus 1. Okay, now if we consider a single molecule, for example, let's say we have HCl or we have CO. Okay, now for a single molecule, if we are talking only about the story of any one molecule, let's see if we talk about HCl, so definitely the H and Cl are having their individual masses, and those masses will be constant. So this moment of inertia, which is nothing else but mu r square, Okay, so the moment of inertia and the bond length also remains the same. Okay, because we are considering a rigid motor over here. So actually what happens for any specific one particular molecule, if you are talking about that molecule only, this moment of inertia also becomes to be as constant. So this 8 is a constant value, pi also has a constant value, I also has become constant over here. Why? Because we are talking about the same molecule. And c is constant, which is the speed of light, and h is also a Planck's constant. So I simply take all these constant terms together and I replace by another term, which is b over here. So it will be, the expression will be bj into j plus 1. Okay, this is my final expression over here. Okay, now so what do we get now? We get an expression where energy Ej, I write over here, is equal to B into J plus 1, where B is the rotational constant. Now this is the rotational constant. Okay, now if we consider any one specific molecule, so what will happen in that case? In that case, the value of B will also become as constant. Okay, why? Because the masses are not changing, the bond length is not changing. Okay, so the moment of inertia is also not changing, so B will be a constant value of that particular molecule. So the energy will only be dependent upon the value of J over here. Okay, so this is what we need to keep in mind from this particular expression number 1 that we have got, is that the energy will now be dependent only on the value of J.